thing you use, basically electronic device. A lot of them include different types of controllers, different types of IC. So the IC actually means integrated circuits. So for integrated circuits, then the basic element inside of the integrated circuit is actually a gate. So such as this figure, the second figure you see here. So you could easily search a lot of different videos to talk of introducing what is integrated circuit. To understand the integrated circuit, to understand the CPU, then of course we have to start with the basic gate logic. So that's why we have to learn digital logic. So we will go back to our slides, and if you feel interested, you could search a little bit more about what is integrated circuit, how the integrated circuit is made. So for additional knowledge, that's not required for this class. But I just want you to know a basic logic gate. A basic logic gate is the elementary unit for the integrated circuit. Is of course the elementary unit for a CPU, for a computer. In this video, we will talk about basic gate logic, including AND gate, OR gate, NOR gate, XOR gate, NAND gate and NOR gate, NOT gate, and NAND gate and NOR gate. So those are all the gates we require you to know. Require you to know the logic, the symbol, how to draw them, and using them to make a small circuit, analyze a small circuit. So first of all, NOT gate. So this thing is called a logic symbol. And this is called Boolean operation, or using a Boolean operator to represent the logic. And this is called, this table, this small chart here is called truth table. This table, the small chart here is called a truth table. So we'll use 3 different ways to represent basic gate logic. So using logic symbol, using Boolean expression, Boolean operator, and the truth table, to represent the same logic, So I require you to know the 3 different ways, 3 different methods to represent the same logic. And of course, you will be using them through all the semester, so you have to know them. And this part, I listed some other notations about hardware programming language. So some of you eventually may go to like hardware related job, and you might want to know more about how to program the hardware, how to design the hardware using hardware programming language. So there are a lot of different types of notation to represent a gate, to represent a basic gate logic. So in a hardware programming language such as Verilog or VHDL, then there's also different ways to represent the same logic, but this is not required for us. I just want to mention that if you read through the reference textbook, some other reference textbook, other material, then you might see them. So you should know what does those things mean, those kind of notation. So first of all, what is a NOT? What is NOT gate? So everybody know the NOT logic. So the NOT logic is actually the opposite of certain condition, right? So, and then in digital world, there's only binary information. So in your current computer IC, most of the IC chip we're using, they're all digital circuits. So what does digital mean? Because we only have either 0 or 1. Right? So then if we want the opposite of the input information, then suppose the input X is 0, then the output Y will be 1. So it is the opposite. So the output is the opposite of the input. So that's why it is called NOT. So this is the basic idea about the NOT logic. And then we use this symbol to represent the NOT logic. And important thing here is there is a small circle, and sometimes you might see this, especially combined with other gates, then you might see only a small circle, and that also means a NOT logic, a NOT logic. So we call this as a logic symbol and a circuit diagram. So that will be something you need to work on in your second quiz. So this is an example of a circuit diagram. So a circuit diagram is formed by multiple gates. We are actually connecting different gates together and then generate the output signal using certain input signal, the different logic among certain input signals. So this is called a circuit diagram. So a circuit diagram is a figure of combining different logic gates, right? So then we have to know a logic symbol. We have to know the different logic symbol for different gates. So the NOT gate is basically trying to perform the opposite, generate the opposite logic of the input. So the Boolean operator is defined as either you put a bar on the top of the input, or you could put a prime near the input signal, and both of them are fine, and both of them are the most popular two different ways to represent the NOT of X. And how to read this? So when we read this logic symbol, or when we read this Boolean expression, so when I have the Y equals X naught, then you could read it as y equals the naught of x, or you could read it as y equals x naught, y equals x naught. And this thing by itself is x naught, or this thing you could call it x naught, or you can call it the naught of x, the naught of x. So what are those x and the y? Those are like the input and output variables. So those are just some variables we use to represent the input-output signal. And of course, you can use whatever letter you want. And normally it is defined using certain letters. So you can call the output as out. For example, the y here, you can call it as out. You can call it as out. You can call it as result. You can call it as whatever variable name. But we prefer to use letters only. We prefer to use letters only. So the last thing here is called truth table. So the truth table is actually a small chart to list the input and output logic relationships. So usually we put the input signal, we list the input signals on the left-hand side and separate the input and the output by a vertical line here. So the last column on the right-hand side is also called, is always called the output. Is always called the output variable. So for this given NOT logic, then the output is y, the input is x, and when your x equals 0, then y of course equals 1. If x equals 1, then y is 0. And remember, we're currently living in a digital world for this class, so we only have binary information, either 0 or 1, either 0 or 1. So suppose I told you this is a NOT logic, then I gave you this chart only with the input. And of course, you have one input signal, one input variable. So the input values could be only 0 or 1, only 0 or 1. And each row is a different situation. And then we should be able to analyze and should be able to list the values for the output variable, the values for the output variable. So the value of the output variable using the NOT logic, because y equals the NOT of x, so then the y has to be 1 whenever x is 0, and the y has to be 0 whenever x is 1. So this is basic information about what is a gate, what is the logic of the gate, and how can we represent. Using 3 different ways to represent this kind of logic. So this is about NOT, logic, and then how this is in your real world. So as the figure I show you by the YouTube's website, at beginning of this video, so when I show you the YouTube website, then you see those kind of IC, and I'm pretty sure you see this everywhere in your daily life. So this kind of IC chip, normally there are different types of gates inside of that, and then such as this IC chip I have as an example here has 1, 2, 3, 4, 6, 5, 6 different NOT gates in it. And then the different pin means different things, such as this is the input and this is the output. This is the input and this is the output of a gate, of a NOT gate, And then of course for IC to be able to work, then you have to have the power, because this is a digital circuit anyway. So have to have the power connected, and you can easily use a small battery, generate the 5-volt voltage, and connect this IC and to make sure it is powered, and then you will be able to have the gate generate a logic 0 or 1. And if you connect a high voltage to this input, and you will get a low voltage from this output. If you connect a low voltage to this input, then you will get a high voltage generated by this output pin. So the different pins here, could be used according to your structure of the IC chip. So this is how it looks like in the real life. And of course, in our class, then we will not be using those, the real stuff, the real hardwares. So of course, then we should know the basic ways, the basic methods, then we could represent this kind of logic, this kind of circuits. So remember, it is the most important, the elementary unit of any circuit, of any circuit. So that's the basic gates, basic logic gates. So the first one is a NOT gate, and the second one is called AND gate. So the AND logic, basically it's easy for us to understand what is AND logic, and you might have this introduced in your mathematical classes, algebra classes. So they all have like different types of logic related with condition, or in your programming class, such as your CS1 or 1030, you might learn logic as well. So the AND logic basically means all the input conditions have to be satisfied at the same time. All the input conditions have to be satisfied at the same time. So for this example, the logic symbol look like this. So if I have two input variables x and y, and both of them have to be satisfied, that means both of them have to be 1. And this way, that's the only way I can guarantee the output is 1. That's the only way I can guarantee the output is 1. Such as you have to turn on the light, and you have to turn on your how to say that? I just want to make a really easy example. Suppose it's raining today, and then you have to put on your boots, and you have to use an umbrella, then to avoid getting wet if you go outside. Or if I send you something through the email, then you have to accept. You have to open your computer. You have to connect to the internet. Connect to the internet. So you have to satisfy all those conditions to get the file I send you through the email, for example. So that's not really a good example, but anyway. So the AND logic means all the input conditions have to be satisfied at the same time in order to get a true result. And then if you would like to use true or false, then I could change the 1 to be true. So in order to have a true result, then both of the inputs have to be true. So if you have one of the input is false, then the output will be false. So the Boolean expression, of an AND logic, usually we will use a dot product. We will use a dot product to represent the AND. But when we read it, so this is of course not a math class. So when we read it, then we should read it as X and Y. And then when we talk about Boolean algebra in future weeks, and then I'm pretty sure all of us will start to read this as X times Y. But we should know that the correct way to read it should be X and Y. Okay, so the output Z equals X and Y, so that actually means the Z could be turned on. Only when both of the inputs are turned on. So if you want to list the truth table, then of course we have two different inputs this time. So the input values could be 0, 0, 0, 1, 1, 0, or 1, 1. So altogether there are four different situations, right? And for different situation of the input values, then the output Z could take different value. This is an AND logic. So only when both of the input are turned on, then the output could be turned on. So that's the only case you will get a 1 for the output Z, and all the other situation, then the Z will be 0. And another way for you to understand this, which is actually what I do all the time, is try to understand the Z is actually generated. By transferring the information from the inputs X and Y, and the Z will be 0. Whenever there is a 0. Whenever there is 1 0, or at least 1 0. Whenever there is a 0, then Z will be 0. The output will be 0. So it's pretty easy. It's pretty easy to for the 0 to go through the AND gate. For the 0 to go through the AND gate. And suppose there is a 0 inside of your inputs list, then the output will be 0. And of course, if there are multiple zeros, if there are multiple zeros in the input list, then the output is guaranteed to be 0. But whenever there is 1 0, there is 1 0 in the input, then the output will be 0. The output will be 0. So the only case then the output can be 1 is all the inputs, they are 1. All the inputs, they are 1. So it's really easy for the 0 to go through the AND gate. The 0 to go through the AND gate. So that actually means to generate a true result, it is really hard, and you have to guarantee all the conditions can have to be satisfied. And then as long as one of the conditions is not satisfied, then the output cannot be true. The output cannot be true. So this is the AND logic. So if you know AND logic, then it's easy to understand the OR logic. So the OR logic basically means as long as one of the conditions, as long as one of the input conditions is true, then the output condition will be true. The output condition will be true. So when you look at the truth table, of course, it's easy to get the 1 transferred through the OR gate. It's easy to get the 1 transferred through the OR gate. And it's hard to get so it's easy to get the it's easy to get the 1 transferred through the OR gate, and it is easy for the 0 to get through the AND gate. So the Boolean expression for the end of two inputs, is represented by x plus y, or x vertical bar y. So this way, the x plus y is used more often. And of course, it's wrong to read it as x plus y. Then we should really read it as x or y. X or y. Okay, so we should read it this way. X or y. So the logic of Z is x or y. And as long as you got a 1 inside of the input list, then the output should be 1. So that's the basic 3 gates for the gate fundamental logic, fundamental gate logic, NOT gate, AND gate, OR gate. The third one, the fourth one is called NAND gate. So even I don't, this is actually not considered as the most important fundamental gate logic, because we could actually generate this gate using NOT gate and AND gate, So the logic symbol, for an AND gate is like a half circle, and the NOT gate look like this, right? So a small triangle followed by a small circle. So to simplify this a little bit, then we could draw it this way. So we using a small circle here to represent the NOT. So what does this mean? So this logic gate basically means it's a combination of the AND and the NOT, So we first do the AND of those two inputs, and then we complement the result. So suppose we have x and y serve as those two inputs, and the output Z here should be the NOT of the x and the y, And remember, we use x product y times y, x times y to represent x and y. So the NOT is basically a bar on top of whatever your input is, right? So it's basically a bar here. So we just borrow that NOT. symbol and put it on top of the product. So don't do this. If you do this, this will be definitely wrong. This is definitely wrong. So this is actually the NOT of your first input, and then you take the whole thing end with the second input. Take the whole thing end with the second input. So this is of course wrong. So the NOT of the product actually means the NAND. So it is the NOT of the end, and then we call it NAND. We call it NAND. So this is the NAND gate. And then, so this is actually the hardware. This thing is the hardware notation, hardware programming notation. So you can ignore this. This is not required for us. So the Z, of course, equals the NOT of XY product. So then we could list the truth table. If you understand the AND logic, you understand the NOT logic, then you should be able to list the truth table. You should be able to list the truth table, because we all know that X and Y, suppose I have the output, intermediate output listed here, and the Z is the NOT of the intermediate output. And the intermediate output here is the X times Y, is the end of XY, is the end of XY. So if I know the value of X and Y, so the end of XY, of course, is 0, 0, 0, 1. Only both of the inputs are 1, then you can have a 1 listed as X times Y. So the Z is the complement of this, So we could easily generate the value of Z and finish this truth table, right? So this is one way we could finish this truth table. Another way to understand the NAND gate is for a NAND gate, only when both of your inputs are 1, then that's the only time you could, all the inputs are 1, only when all the inputs are 1, then that's the only time we could generate a 0. That's the only time we could generate a 0. So that's the meaning of the NAND gate. So if we have NAND gate, then we should have a NOR gate. So for an OR gate, then the logic symbol looks like it's kind of like a little bit curved triangle, right? So we could have a NOR gate. So it's basically a combination of an OR gate followed by a NOT.